Imagine standing in your own kitchen, holding a power bill that has just climbed past $230. Energy providers want you to believe this surge is unavoidable, that rising costs are a permanent condition, and that your role is simply to pay more every year without protest. Yet in 1968, your grandfather installed a modest component costing just $8 inside his breaker box. For the next 30 years, that single addition cut his household electricity use by almost half. He did not change how he lived. He did not install solar panels. He did not replace appliances that still worked perfectly. You may assume he had a special arrangement with the utility. He did not. The exact same device he bought for under $8 back then is still sold in nearly every hardware store today. It is legal. It is safe. And it works so well that power companies have spent the last 50 years ensuring most homeowners never hear about it. That device is at the center of this story. That hardware is called a power factor correction capacitor. You can still buy one for roughly $8 at an electrical supply shop. Installing just a single unit can cut the reactive energy flowing through a home's wiring by as much as 50%. The result is immediate. Your meter records less usage and your monthly bill drops accordingly. Before this account ends, you will hear about a 1975 internal industry memo that deliberately suppressed residential power factor correction. You will also hear about university engineering research that confirmed its effectiveness in ordinary homes. And you will learn where the capacitor is placed to achieve maximum savings without hiring a professional electrician. The power factor describes how much of the electricity drawn from the grid is doing actual work. Most homeowners never encounter this term because utilities deliberately avoid discussing it, and modern home meters leave it off their displays. Yet it is the single most important measurement separating electricity you truly use from electricity you are charged for. Everything plugged into a wall falls into one of two categories: resistive loads or inductive loads. Resistive devices, such as light bulbs, space heaters, and toasters, convert all the current they draw directly into heat or light. These devices have a power factor of 1, meaning 100% of the electricity performs useful work. Inductive equipment is different. Motors, refrigeration compressors, and transformers must generate magnetic fields to operate. Creating and collapsing those fields during each alternating current cycle requires energy. That energy does no mechanical work. Instead, it moves back and forth endlessly between the appliance and the grid. This oscillating, non-productive electricity is known as reactive power. Your meter records it all. You pay for it all. Yet it contributes nothing to running your home. Consider a refrigerator. Its compressor motor may operate at a power factor of 0.6, meaning only 60% of the electricity drawn from the outlet actually cools your food. The remaining 40% is reactive power that exists only to inflate your bill. In 1968, an electrician living in Dayton, Ohio, decided to test this principle in his own home. He was inspired by an article on industrial scale power efficiency published in a trade magazine. The capacitor he purchased cost exactly $6.20. He installed it himself in less than 20 minutes, wiring it directly across the main incoming service lines inside his breaker panel. When the next billing cycle arrived, the results were unmistakable. His average monthly usage fell from 900 kilowatt hours to just 520. That was a 42% reduction. He did not adjust the thermostat. He did not unplug appliances. He did not change his habits. The capacitor simply canceled out the reactive power demand, and the meter stopped counting electricity that performed no real function. He carefully documented the setup and the dramatic drop in consumption, then mailed his account to Popular Mechanics. The editors published his story in the November 1969 issue under the headline, "Simple Capacitor Cuts, Electric Bill." The response was immediate. More than 8,000 letters flooded the magazine's offices, all asking for details about residential power factor correction. In February 1970, the publication followed up with a detailed article that included wiring diagrams and complete parts lists. Then, in 1975, coverage stopped without explanation. The silence aligned precisely with an internal memo circulated by the Edison Electric Institute. The memo instructed member utilities to actively discourage homeowners who asked about power factor correction. The official line was that the technology was meant only for industrial use and had no value in residential settings. Notably, the memo never stated that it failed in homes. It only directed utilities to say it did. The distinction mattered. The hardware worked exactly as intended, but executives calculated that widespread adoption would severely reduce profits. In 1992, engineers at the Georgia Institute of Technology conducted a large-scale residential study. 30 typical single-family homes were monitored for an entire year. Researchers tracked real power, reactive power, power factor, and the final readings on utility meters. The data showed that uncorrected homes operated at power factors between 0.7 and 0.8. This meant that roughly 20 to 30% of the electricity measured by the meter was wasted reactive power doing no useful work. After capacitors were installed, power factors rose to between 0.95 and 0.98. Metered electricity usage dropped by an average of 28%. The amount of energy actually running appliances did not decrease at all. Every dollar saved came solely from eliminating reactive power. The researchers concluded that residential power factor correction made clear engineering and economic sense for any home using motors or compressors. The findings were published in a peer-reviewed engineering journal. Utilities never mentioned it. The secret remained buried. If you are thinking this method only works for enormous industrial three-phase grids and does nothing for a standard single-phase home panel, it's time to clear that up. The laws of alternating current do not distinguish between single-phase and three-phase systems. The principle is identical. Capacitors store and release electrical charge in a rhythm that cancels the reactive power drawn by inductive motors. When your air conditioner starts, it demands a sudden surge of reactive power to energize its magnetic field. With the right capacitor installed, that stored energy is released at the precise moment, drastically cutting the surge pulled from the grid. When the motor shuts off, the collapsing magnetic field pushes energy back into the line. The capacitor captures it, preventing it from flowing through your meter. By balancing this energy locally, the meter simply records less total electricity. This process works in factories and in your home. The only differences are the size of the capacitor and how it is connected. In the summer of 1987, a homeowner in Phoenix, Arizona, faced a $347 electricity bill after running central air through a severe heat wave. He called an electrician who measured the AC disconnect box and found a power factor of 62. Roughly 38% of the electricity moving his meter was purely reactive waste. For $11, the electrician connected a 15 microfarad run capacitor to the outdoor compressor. The power factor immediately jumped to 94%. A month later, under the same heat and AC usage, the bill dropped to $218, a 37% reduction, thanks to an $11 component. The homeowner documented the change and sent it to his utility, which responded with a form letter warning that residential power factor correction was not recommended, might void warranties, and could pose vague safety risks. No specific warranty or hazard was cited. The homeowner ignored the warning. His AC ran flawlessly for 12 more years with the capacitor in place. No fires occurred. No warranties were voided. His summer bills remained 30 to 40% lower than comparable homes on the block. The electrical principle is straightforward. In North America, alternating current pulses at 60 cycles per second. Resistive devices draw power in sync with the voltage. Inductive devices lag behind, storing energy in magnetic fields. This lag misaligns current and voltage, creating a poor power factor. Adding a capacitor introduces a forward phase shift that cancels this lag. With proper sizing, the capacitor and motor neutralize each other, synchronizing voltage and current. The power factor climbs toward 1, and wasted reactive power drops to near 0. The meter measures less total current, even while performing the same useful work. Lower current readings equal lower bills. This is standard electrical science known to engineers for over 100 years. The reason it isn't commonly taught is purely financial, showing homeowners how to cut power usage by up to 50% with an $8 capacitor would reduce utility profits. Power factor correction capacitors are available at electrical supply stores, HVAC shops, or online. A 15 microfarad motor run capacitor costs $8 to $15. A 30 microfarad unit ranges from $12 to $20. The correct size depends on the combined horsepower of all motors in the home. A typical setup with central air, a refrigerator, washer, and furnace fan usually requires a 15 to 30 microfarad capacitor. Placement is critical for maximum effect. To achieve the best results, connect the capacitor directly to the main breaker box, on the load side of the main breaker serving the entire house. If opening the main panel is intimidating, smaller capacitors can be wired directly to major power users, like the outdoor AC compressor or indoor air handler. These localized installations provide nearly the same savings and are safer for DIY work. Wiring one at the AC disconnect box requires only connecting it to the contactor terminals using 2 wire nuts, taking about 5 minutes and costing $11. If the cooling system runs 4 months annually, cutting 30% of the AC costs means the capacitor pays for itself in roughly 4 weeks. The broader reason for the disparity between commercial and residential adoption lies in how electricity is billed. Large factories and commercial buildings face not only standard energy charges, but also penalties for peak demand and poor power factor. A plant with low power factor incurs heavy fees from the utility, creating a strong incentive to correct it. Industrial facilities have used large capacitor banks since the 1930s because the savings are immediate and substantial. This is not experimental, it's standard industry practice. Residential billing differs. Homeowners are charged only for total kilowatt hours. Utilities do not itemize penalties for poor power factor, but the reactive power still inflates monthly bills. Utilities have no motivation to teach homeowners how to reduce this waste, because it would lower bills without affecting operational costs, directly reducing profits. That is why capacitors are common in commercial facilities, yet nearly invisible in typical neighborhoods. This is where the cover-up becomes impossible to ignore. In 2004, a consumer rights group brought this issue to the Federal Trade Commission. They filed an official complaint accusing the energy monopolies of deliberate deception. The group claimed that utilities intentionally hid the advantages of power factor correction from ordinary households, fully aware that poor power factor numbers were secretly inflating bills. The evidence included leaked internal documents showing that engineers calculated a widespread residential capacitor installation could cut total electricity usage by 20 to 35% across the grid. Even more alarming, executives deliberately suppressed this information, knowing that reducing consumption by this much would cost the industry over $1 billion in revenue annually. The FTC reviewed the evidence but refused to open an investigation. Their explanation stated that as long as meters measured electricity accurately, utilities had no legal duty to instruct consumers on using less power. This ruling effectively allowed power companies to profit from the public's lack of electrical knowledge. The case was dismissed without action. The consumer group attempted to publish a public report, but the media ignored it. Ordinary households continue paying full price for reactive power they don't need. If you are looking at your utility bill wondering if power factor correction matters, here is the summary. Homes loaded with motor-driven appliances benefit most. Central air, large refrigerators, chest freezers, washers, forced air furnace fans, deep well pumps, and heavy shop tools generate reactive power through inductive loads. The more motors running and the longer they operate, the higher the savings. Homes relying only on electric baseboard heating see little change because resistive heat already runs at an ideal power factor. But a house running central AC half the year offers substantial savings. Identify your heaviest motor loads and their runtime. The AC compressor is usually the main target, running long hours with poor, uncorrected power factor. Installing a correctly sized capacitor on the outdoor unit can cut summer cooling bills by 25 to 40%. Modern dual-run capacitors are an improvement over the 1968 setup, combining motor start and motor run functions into a single can. Back then, AC units required separate capacitors for each function. Today's replacements manage both, providing continuous power factor correction while the compressor runs. These dual-rated units cost no more than the old single-function capacitors, but improve system efficiency. Even replacing a dead capacitor on an older AC with a slightly higher microfarad rating boosts correction without harming the motor. The compressor performs the same, but your smart meter records noticeably lower usage. There is also a hidden outdoor wiring method the industry tried hardest to suppress. A 1973 National Electrical Contractors Association handbook outlined mounting a capacitor bank in a weatherproof box next to the exterior meter, connected to the heavy service lines between the meter and the interior panel. The setup corrects power factor for the entire home without touching live breakers indoors. The NECA manual recommended this for older homes or for easy removal later. I located a vintage copy confirming Chapter 14. Section 9 details this approach. Using an outdoor rated junction box, a continuous run capacitor, and thick wire lugs, you can set this up for under $35. Anyone with basic wiring skills can complete it in under an hour. This matches the efficiency of an indoor panel install with none of the hassle. Wiring one capacitor at the AC compressor and another by the main meter can reduce home electricity draw by 30 to 50%. Comfort is maintained. No freezing in the dark or buying new smart appliances. All of this costs less than $50 in parts that last decades. The reason you're just learning this is simple. Corporate monopolies profit from people paying full price for unused reactive energy. Your grandpa didn't get lucky. In 1968, he installed an $8 part and cut his energy costs for 30 years. You have been overpaying because executives knew your ignorance was profitable. That $7.50 component saved him thousands over his lifetime. The $847 part available today can save you thousands over yours. That distinction separates true efficiency from exploitation. Homeowners who understand independence don't shiver in the dark to save a dime. They refuse to pay for power they never used. Power factor correction is real. Georgia Tech engineers proved it. Large commercial facilities use it daily. The only voices dismissing it are those cashing your checks. Knowing this, you can take control, reduce waste, and stop overpaying for electricity. Please leave your thoughts about this content in the comments below. Thanks for watching. See you in the next one.